but violent like Ben Siegel. I'm anti-evil, plus I touch a desert eagle. My life's illegal, slaves in prisons are equal. The devil's lethal, he killed 100 million people. I'm Darkman, Iceman, La, Wu-Tang Clan, Trafficante, Sensei, Comprende. My Marine Corps, straight from the Trojan War. Black Cape Crusader, trapdoor, flamethrower, stuck a chain store when I was dirt poor from Mobby War. Next week the Germans had me on the bulletin board. I beat that case, they couldn't identify my face. I'm triple darkness, silencer I have you erased. Me and my Wu pirates start riots with Osiris. Math, I apply it, kill you, but I'm quiet. Respect the abbot, it's love or lost. Shine like a shooting star, sting with the cobra claw. What? Boom world order, 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 boom world order.
Yo, I enter through the cave of your ear in a high-pitched silent tone only a dog could hear and impregnate you with the wisdom of the woo. Then your subconscious dreams come consciously true. Have you in such deep thought, your pulse and blood pressure so low, you diagnosis corpse, having out-of-body experience, clear no interference, everything with physical form, lose appearance, become one with the formless. Now you feel your strongest, escape travel lives, you live for the longest. Love 1,000 years in a day, without opening your mouth you say everything you wanted to say. Attracted to the core of the earth, I stay grounded. The sun in the center of this, I'm surrounded by planets in the mist that spins the wind chill. But my light melts a snowflake for 93 mil. All who have an ear, let them hear as we build. Cause one ear of corn can produce a cornfield, and one cornfield can produce the cornmeal. The bread from the body of Christ, all is filled with the truth of life inside your bone marrow. You can make it physical as large as your shadow. Whether space is cyber or optic is fiber, become a Wu multimedia subscriber and hibernate the root tape in your mental state. Let it meditate. Sit back then await the orders. For this you don't need no tape recorder. So let's prepare for the Wu world order. 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 We coming soon and we striking at your borders.
All right, so I wanted to finish up what we were doing on Friday with this demonstration of a connection pool. Remember what we did is we set it up so that there were 10 persistent connections. And when we initialize this, we create those 10 connections and put them into this actual connection pool. That connection pool is modeled using what's called a blocking queue, and we'll see why that's necessary here in a second. But basically, think of it as a line, right? At the front of the line, when we need a connection, we get a connection and take it from the front of the line. We don't close the connection when we're done with it. Instead, we return the connection by offering it at the end of the line. So these connections are being used and then reused and reused in this kind of churning kind of connection pool. We do have this shutdown method that goes through, and for each connection that should be there, it tries to take that connection and then it closes the connection. The reason that we go through this this loop and we need to take those connections is because there could be 5 of them in there, right? Then 5 of them are being checked out. So if I've closed 5 of those connections, I need to wait until those other connections have been checked back in order to close each and every single one of them. I want to make sure that I'm closing all of those connections. The reason that we use take and offer is because it blocks. Again, this is called a blocking queue. So, for example, if we have no connections at all in this queue, but some thread comes in and says, I need a connection, can I please have one? Right? It says, no, there are none to check out. I'm going to block you. I'm going to put that thread to sleep until I have a connection that shows up that they can check out. Then I'll wake that thread up and say, hey, there's a connection there, you can take it, and then it checks it out for it. All right? That's going to be absolutely necessary if we do things in a multi-threaded environment. Right? Let me show you what the experiments that I've set up here for. Here's the demo. All right? So here's the first experiment, which is a sequential demonstration. What I'm going to do is for a number of persons, which I've set to be 1,000, I'm going to insert 1,000 copies of Agent Smith here. Right? And I'm going to do it in a sequential manner. Right? In fact, I'm going to just start this because it's going to take a while. Right? Remember that what insert person does here. It creates its own connection every single time. It inserts the person, and then it closes the connection. Right? So doing this for 1,000 random people is going to take quite a long time, even though I'm on campus. When I was off campus, this took like 4 minutes. Right? It's probably only going to take 2 or 3 minutes here, but we'll let that run while we look at everything else. The next experiment that I'm going to run after this is going to take way faster. Right? Instead, it's going to do 1,000 in sequence, but we're going to use this connection pool. Let me show you the difference there. Instead of opening up its own connection, it gets a connection from the pool. Remember that opening up these connections, oh there, it's 40 seconds. Let's go ahead and record that, right? So it's going to take sequential, right, is going to take 40 seconds. Right, it took 4 minutes from off campus, but it's going to be way quicker now because we're on campus. But opening up and closing those connections, that's going to be one of the most expensive things you can do. If you can go ahead and pay up front for the opening of 10 connections and then just reuse them, that's going to be way quicker. Let's see. So I've got, I'm going to go ahead and get rid of that demonstration and go ahead and do this demonstration. So remember it was 40 seconds before, but now because we don't have to open up our own connections every single time, it's going to be a little bit quicker. Right? There we go. 7 seconds, 7.25 seconds. So with pool, right? Look at that speed up already, right? It's what, 4 or 5 times faster, or 6 times faster, right? Just because we don't actually close any of those connections. Now what I'm going to do is I'm going to show you what happens if you leverage all of those PDC concepts that we covered last semester in those extra modules. What I've done is I've created a parallel pool. So I'm going to say that I'm going to still go ahead and insert 1,000 copies of Agent Smith there, but I'm going to distribute that work among 10 different workers, right? Let's take a look and see what that looks like. I'm creating what are called a bunch of runnables. These are things that can run independently in their own thread. Each one of them will be given a part of that task. So for example, there was 1,000 divided among 10 workers means that each one is only going to insert 100 people instead of 1,000 people. I create this executor service, which is going to create it with 10 threads here. That actually should be num workers, but I'm going to go ahead and leave it there. And then what I do is I let it run. I add them all to, and I tell the executor, go ahead and start executing those. Right? I do need to make sure that they all get done, so this is just a technical thing where I block until everybody is done. Then I shut down the connection pool and I shut down the executor service. Right? I don't want these things happening before everybody is done. All 10 of those threads that are acting in parallel, I don't want to suddenly close it until, 5 of them are done, but 5 of them are still running. I don't want to close everything down on them. Right? So I wait until everybody's done here. All right, let's go ahead and run it with 10 connections and 10 threads. 1, 2, not even 2 seconds. 1.69 seconds. Right? Before it was 7 seconds. So you're not going to get 10 times speed out of it because you're still, you still are doing stuff, but it's pretty dang close. Right? What if I only had 5 connections and 10 threads though? So what I mean by that is let's go over to the connection pool here and let's limit it to only 5 connections now. Now think about that before we run that. Right? Are all 10 threads going to be able to do things at the same time? If only 5 of them are able to check out connections, then we've got 5 threads here sitting waiting to check out another connection. So what's going to happen here? More time or less time? More time. Right? In fact, significantly more time. There we go. It's still better, but 3.14 seconds. Right. There we go. All right, what if we did 10 connections? So let's go ahead and restore that to 10 connections, but we didn't have as many workers. Suppose that instead we had 5 workers here. So now each one of them is doing 200 inserts instead, but 10 connections. There are more than enough connections there for them all to use, right? But there are only 5 people working, so it's going to be 3.24 seconds. So, when did you get the most performance? When everything was balanced. Every single thread had its own resources. You didn't have a thread sitting there waiting for a resource, just sitting there idle, being asleep, twiddling its thumbs. You didn't have a connection sitting there being open, wasting resources, not being used. It's when everything is in balance. Now, do you remember back to that PDC demo that you did last semester? And there was this producer-consumer thing. If you did it, if you were in 155H or 155E, you did it, right? Hopefully, I have a forthcoming paper on all of your results, by the way. At IPDPS, I think. So EduPar, right? It's a PDC Education Conference, right? And so, you saw everything worked if it was in balance. If we had 3 consumers and 3 producers, it would be producing requests and it would be able to handle those requests evenly. But if we had more producers, then the number of requests grew, and then the number of consumers couldn't handle all the work. Versus if we had more consumers than producers, then 3 producers were sitting there idle all the time, not doing anything. It's when these things are in perfect balance that we get the best performance, right? 2 seconds instead. In fact, I could bump this up to 10,000. Let's make sure that we've got 10 workers here, right? And we'll still see a pretty good performance improvement here. Now, this is an order of magnitude greater, 10 times as long, and before it was only 1.69 seconds. So I'd expect it to take about 10, 11 seconds here now. Maybe a little bit more, 20 seconds. Right? Oh, there, 8 seconds, right? We go up by a factor of 10 there. If we went up by a factor of 10 here, we're not going to get the same performance because only one thread, or my processor here, I think is like 8 core, but with multi-threading, it's 16 processes. So at most, 16 processes can be running at any one time. Move this over to the server, and there are 48 cores or 64 cores, and now you can have 64 threads running at once. But at some point, you run out of threads, right? So 10 is probably okay, because there is actually a main thread here too that's executing. Right? And now you start seeing the real performance here, right? Before, again, off campus, it took me 4 minutes because of the network lag, right? We saw that opening and closing connections, that's a huge amount of resources, right? We were able to just simply by not closing our connections, we were able to speed it up by a factor of 6. By increasing the number of threads and increasing the number of connections, we were able to get it up even more, right? Where I'm doing 1,000 database transactions in only 1.6 seconds. Right? Do that on the same server, and it's probably a fraction yet again. So this stuff matters, right? Especially if you're doing a larger application where you are doing thousands or tens of thousands or millions of transactions per second. Right? All right. Any questions on that? Because that's a kind of one of those extra things that we cover in the 8 section that we don't cover in the main section. Again, if you want to do connection pooling, go ahead, but you're not using multi-threading, so you're not going to get anything out of it, right? It would be like setting the number of connections to 1 and then setting the number of workers also to 1 because you're not actually using any threading, right? Okay. All right. And by the way, that'll probably jump us back to what? 7, 8 seconds there to do 1,000. There's one runner, and they're responsible for everything, and so it's going to take what? Yeah, 6.5 seconds there, right? All right. No questions on that? Cool, or at least, right? All right. So back to the mundane. Actually, this is the kind of stuff I do like. Asymptotics, right? Going to be a lot of math today. Okay. So a little bit of calculus too. Remember that we have this 5-step process where we want to analyze an algorithm. So the setup is going to be identifying the input size, and the elementary operation. Once we've got this set up, then we do the work to determine how many times the elementary operation is executed with respect to the input size. Step 5 here is something that we've not covered and that we're going to cover now. We characterize that function from step 4 in terms of big O analysis. Right? And that's going to be step 5. Our motivation here is that we don't want to worry about the small constants, the lower order terms or the constants. Our motivation is that we want to characterize an algorithm's performance or efficiency with respect to the input size. We want to ignore lower order terms and any constants. Right? We want to know what the order of growth is. We want to focus on the order of growth or rate of growth. Right? Those constant terms, again, you can upgrade your hardware, and now each operation takes half as much time. Those constants then change. Who cares? The lower order terms they're going to grow, but not grow as fast as the largest order of term. We want to know what that is, and we want to give it a characterization. We're interested in an algorithm's performance as n tends towards infinity. Larger and larger and larger input sizes. Right? We don't care if something performs well on small input sizes. Right? And the tool that we're going to use for that is big O analysis. Big O analysis. This tool goes back way before modern computing. It goes back to Leibniz. He invented calculus, right? Leibniz? No? No? Okay. I think it was Leibniz that created modern calculus. Newton, yes, but Leibniz actually created the actual tools, right? And so this goes all the way back, a couple hundred years here. I'm not going to give you the original calculus definition. Instead, I'm going to give you the more modern algebraic definition. Let f of n and g of n be two functions. For our purposes, they characterize the performance of two algorithms A and B respectively. We say that f of n is big O of g of n if there is a positive constant c and an integer n naught such that at some point, f of n is always going to be less than or equal to c times g of n after that point, for all n greater than or equal to n naught. Okay? Don't worry about the definition immediately yet. Instead, think about an example here. In fact, here are my two functions. Let f of n, come on, there we go. Let f of n be, 175 n squared plus 50n plus 1. And let g sub n be n cubed. Now, first of all, just tell me what your intuition is. Which one of these functions is larger in terms of rate of growth? G of n, right? Why? Because it's a cubic. And as we all know, polynomials, a quadratic and a cubic is going to grow faster. Okay? Now, let's graph it. I've already done that over here. Right? There's 175n squared plus 50n plus 1 n to the cubed, but I've focused my attention here on 0 to 100. What's the lower one? Right? Remember, lower is better because that means fewer resources. Right? The lower one here seems to be n cubed against our intuition. Right? But that's just because I'm looking at input sizes of 0 to 100. If I zoom out and look at input sizes 0 to 200, we see that at some point the performance changes. Yes, up to that point, n cubed performs better. But after that point, that function will always dominate. In fact, if I zoom out to 1,000 here, that crossover point almost disappears all the way down here somewhere, right? And certainly this one is going to be greater always, always after that point, right? Whatever that point happens to be. After that point, for all n greater than or equal to that point, this inequality holds. That this one will always be on top of this function over here, right? Now, how do we quantify all that? Right? Again, big O characterizes the rate of growth of two functions. We often write that f of n is equal to order of g of n. Right? But that's an abuse of notation there. Have you covered this in 235 yet? No? Okay. Well then, in 235 you might look at it differently, right, and use set notation. You have covered this in 235. Why? Because the thing on the right-hand side is a class of functions. All functions such that they're bounded by g of n. Right? The thing on the left-hand side is a function, so that function is a member of that set of functions. But it is so common to just write that we do. It's an abuse of notation, yes, but it's the same meaning, right? Or its meaning is understood. Right? What we say is that f of n's rate of growth is bounded above by g of n's rate of growth, right? That g of n, another way of putting this is that g of n's rate of growth is at least as big as f of n. Right? Note here, this is a less than or equal to. It's not tight. Right? This is not necessarily a tight characterization. Right? For example, if I write, say, 3n plus 3, right? That's going to be equal to order n. Right? That is tight. This is tight. Why? Because the thing on the left-hand side is a linear function. The thing on the right-hand side is a class of all linear functions. They match. Their order of growth matches. But if I were to say 3n plus 1 or plus 3 is equal to order n squared, that's also true. N squared. There we go. Right? This is true, but not tight. It's loose. Right? Why? Because it's greater than or equal to. Right? So g of n can have a greater growth, a strictly greater growth. It would also be true if I wrote, that it's cubic, or it's bounded by a cubic, I should say. Right? It would also be true if I said that it was bounded by a exponential. Bigger, 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 bigger. Who cares? Right? That's because it's not a tight characterization. But what is absolutely not true is if you reversed any of those. N squared is not order n. Right? This is not true. Right? Because you can't just go and flip those two. Right? There is another characterization in 235 if you cover this, big omega. Right? So it is true that n squared is omega, there we go, of n. Right? There we go. That's the definition, but in reverse. Right? It provides a lower bound. This is a lower bound. Right? That's a lower bound definition. And it's big omega. This is, by the way, is big omicron, which is big O. And then there's also another one. This is more true, that 3n plus 3 is theta. This is big theta of n. Right? That's a tight characterization. That's saying that they have an asymptotic equivalence. The growth rate of the thing on the left-hand side is equivalent to the growth rate on the thing on the right-hand side. And that's big theta right there. Right? We're not going to go through those. Instead, we're going to restrict our attention to big O. Right? Okay? All right, so proofs. Right? How many proofs have you done in 235? A lot? Proof. No? I'm seeing yes, I'm seeing no. Maybe it depends on which section you're in, maybe. Right? So given two functions, f of n and g of n, all right, there we go. How do you prove that f of n is big O of g of n? Right? It's not just, oh, well, I feel like this one has a higher order of growth, right? The first step is that, right? First step is to express your intuition. So for example, let's come back over here to these two. You already expressed your intuition. Our intuition tells us, our intuition says that f of n is big O of g of n. And we're going to set about to prove that, because we need to know what are we trying to prove before we try to prove it, right? And I'm going to try to prove this. What if it were the other way around? What if I said that, no, that's g of n and that's f of n? Right? Go ahead and flip them around, right? F and g are just names. Just go ahead and rename them, right? So that it looks like that, okay? I'm going to give you 3 different techniques here. Actually, here's my first, 2 algebraic techniques first, right? And then we're going to look at the calculus technique, right? Approach A, right? Find the crossover point, right? That is the largest value of n for which the 2 functions intersect, right? In other words, they have the same value. They have the same value. Okay? Now, why is that going to help us? Let's come over here. Let me go back down to 200. If you find the point at which they intersect, and it's clear that one is monotone increasing over the other, then you can say that after that point, they will never converge again. They will never intersect again. Then all you need to do is look at it visually or look at it algebraically and say, okay, they clearly diverge from that point at that point, and then this one is always on top. And they never meet again, right? This one will always be on top. So it's enough to find this point and then analyze it after that point. Right? Help me out with this one. What is our crossover point? Oops. Crossover point. How do I go about finding that? How do I go about finding when 2 functions intersect? They're equal. Good. For what values? For what n? Right. Okay. So let's go ahead and try to do that. 175 n squared plus 50n plus 1 is equal to n cubed. Yeah. Ugly. Right. Let's go ahead and take the other one to the other side. 175 n squared plus 50n plus 1. Oops, sorry. That's minus is equal to 0. Right? So I need to find the n's that satisfy this. What am I trying to find? We call those things roots. We need to find the roots. Right. Now, does anybody remember off the top of their head how to find roots of a cubic equation? Nope. In fact, there are several steps you have to determine. There's a case A, and then if that doesn't work, case B, and then there's a plug and chug thing. Right? I don't want to do that. So I'm going to simplify this immediately and take away that 1. Right? Why? Because it's just a constant. We're off by 1. Whatever analysis we come up with later on, it's still going to be the same analysis. It's just off by 1. Right? At the end of the day, we're going to come out with this with the same conclusion. Right? This is why often, even in mathematics, right, they give you these equations where everything turns out to be nice instead of some random value that has 50 decimal points or something. They make it so that everything comes out to a nice integer function or something. Right? All right. Now what do? Still don't know how to do this as a cubic, but you can factor out an n. Right? Oops. N being 0. That's one root, right? Because if n is 0, this goes to 0, 0, 0, and that's equal to 0. All right, great. That means I can factor that out. N squared minus 175 n minus 50 is equal to 0. Now do you know how to do it? What is it? Negative b plus minus square root of b squared minus 4ac all over 2a. I don't want to do that. Right? So instead, what I'll do is I'll come over here to Wolfram alpha. Right? Wolfram alpha. I don't want to lose that other one though. So Wolfram Alpha is nothing more than a web interface to Mathematica. So n squared minus 175n minus 50 roots. Give me those roots. All right, I've got this one, and I've got this one. Tell me about this root right here. Negative 0.28. Where does that come out over here? Let me zoom in even further to -1 up to 10. There we go. And indeed, those two functions indeed are intersecting over here. I'd have to zoom in even further. Let's just go down to 1. They're intersecting right there. See it? Does that root matter? Remember, what are we doing? Don't lose the forest for the trees. We're analyzing this with respect to input sizes. Is there an input size of negative 0.28? No. This one is completely irrelevant. Right? So I'm going to immediately ignore that root. I'm going to focus on the largest root. The largest root here being 175.285. N equals 175.285. There we go. That's the root I want. The n being negative 0.28, irrelevant. These two roots are relevant, but this one is the largest one. Right? So, for n naught being 176, why did I go up to 176? Remember, it was 175.285. What was the definition again? Or where's the definition? There we go. An integer and not. Why an integer? What is this quantifying again? Input sizes. Is there an input size of 175.285? Nope. So what I'm going to do is I'm going to go up to 176. For n being 176, and implicitly here, c is equal to 1, f of n is less than or equal to g of n for all n greater than or equal to n naught, which is again 176. Right? Just because of my work over here, showing this work. And then of course, I cheated and used Wolfram Alpha there. Right? Again, 175 n squared plus 50n plus 1 is less than or equal to c being 1 here, 1 n cubed, but we don't write that 1. Right? That's technique A. Let me give you another one. N to the 50 plus 7 n to the 39 plus 8 n squared minus 3n plus 1 versus n to the 100. Do you want to do the same technique for those? How many roots would you end up having to find? Most of them would have multiplicity, multiple multiplicities, but 100 roots, right? I ain't doing that. Right? That's terrible. So that's where, if this approach works, A works really well for simple polynomials. Not so much for higher order polynomials or logarithms or exponentials, etc. Right? Do you know of any equivalent quadratic formulas for exponentials to find roots of them? No, that would require some numerical analysis techniques. So let's go with approach B. Right? What I'm going to do is I'm going to fix n naught to be 0 or something small and find a constant c such that the inequality holds. Right? So now let's understand what I mean by that by coming back over here to the graph. I am plugged in, right? Yeah, we're good. All right. Let's come back over here to the graph. Okay. And let's go ahead and come back down to 200. There we go. From 0. There. All right. I don't want to find this crossover point. What I want to do is I want to change the crossover point. I want to make this function bigger. Right. Let me go ahead and make it twice as big. How will that change the function? Does it change the rate of growth of the function? Careful, just multiplying by a constant. Does that change the first derivative? I mean, it changes it to 3 instead or whatever, right? But it doesn't change the fact that it's still a cubic function, right? But what did it do to this crossover point here? It moved it down over here. Keep going. What if I made it 3 times bigger? Where's the crossover point now? It's somewhere over here. It went from here to somewhere over here. I wish this would, I guess, can I enlarge it? If I pay for it, no. All right, so what I'm doing is I'm changing the crossover point until it becomes 0, right? By me simply making it bigger and bigger and bigger, right? This is really, really easiest technique. Why? Because all you have to do is set up an inequality and make the right-hand side bigger and bigger until it equals g of n. All right. So let's take a look at it in practice here. Get rid of all this. We want to show that 175 n squared plus 50n plus 1 is less than or equal to c times n cubed, right? For some c for all n greater than or equal to 0. Okay? What I'm doing here is I'm fixing this one. I have 2 unknowns, c and n naught. Both of these techniques involve fixing one and finding the other, because there are an infinite number of pairs for which that inequality will hold. Right? We just need to find 2 of them, right? 1 pair. Right? Well, okay, I can't start off immediately like that. That's what I want to show. So I'm going to move this down here. That's what we want to show. How can I make this thing bigger so that eventually it looks like this? I've got 1, 2, 3 terms here and only 1 term here. So I want to start collapsing these terms by making them bigger. What could I do with 1? I could make it 2. I could make it 3. I could make it 4, right? I'm always making it bigger, right? But what else could I make it so that I collapse it in onto one of these other terms here? N. 175 n squared plus 50n plus n, right? Now, does that hold for all n greater than or equal to 0? Careful, no. It all holds for all n greater than or equal to 1. Right? Again, you just have to show a pair. It doesn't necessarily have to be 0. 0 is just my starting point. I'm going to increase that to 1. That's equal to 175 n squared plus 51n. Okay? I've now taken it down to 2 terms. I'm still not there, and my terms don't look like n cubed anymore. All right, still not yet. Right? Make it bigger. 175 n squared plus 51 n squared. All right. Is that true for all n greater than or equal to 1? Yeah. All integers n greater than or equal to 1. So that's equal to 226 n squared. All right. Looking kind of like this. We've got a constant and we've only got 1 polynomial term there, but it's not the right polynomial term. Can I say that that inequality holds? In general, no. Right? But for all n greater than or equal to 1, yeah. Right? Because if I go to negative, then obviously this one's going to be less because it's going to end up being negative, because negative times negative times negative is going to be negative. But guess what? I don't have negatives because my inputs are input sizes. My domain is input sizes. Right? Oh, so 226, sorry. 26. There we go. All right, there. That's equal to c times n cubed, which is where I wanted to be. All right? So my conclusion is that for c being 226 and n naught being 1, the inequality holds, and f of n is big O of g of n. Right? That's technique B. Now, put on your calc hats for the rest of the day. Let's look at technique C. Technique C, set up a limit of the two functions. For that, I'm going to go ahead and copy this because it's a big giant LaTeX thing. Does it? There we go. Limit as n tends towards infinity of f divided by g. If the limit converges to 0, then we can conclude that f of n is big O of g of n. Why is that? It converges to 0. What does that mean about the thing on the top? It's growing small, and then the thing on the bottom is increasing in size, outstripping the one on the top, because the denominator, big denominator, means small values. And so it converges to 0. If the limit diverges, that means that just the opposite. The thing on the bottom is growing slow, and the thing on the top is growing fast. If it converges to some constant c, then that means that they have a steady rate of growth with each other. And so we conclude that f of n is big theta of g of n. Again, don't worry about that. That just simply means both f of n is big O of g of n and g of n is big O of f of n. Do I have everything balanced? Looks like it. Oh, no, I don't. Extra one there. There, now we've got it. All right. Okay. So let's go back over here and do it again. Third proof technique. Set up your limit. Oops. Limit as n tends towards infinity of 175 n squared plus 50n plus 1 all over n cubed is equal to what? What would be your first step in solving this limit here? Break it up algebraically. The limit of sums is equal to the sum of limits, provided that they converge, and here they will. Limit as n tends towards infinity of 175 n squared all over n cubed plus the limit as n tends towards infinity of 50n over n cubed plus the limit as n tends towards infinity of 1 over n cubed. What about this last limit here? You have a constant on top and a monotone increasing function on the bottom. What's the limit? 0. What about the second one? Here, algebraic cancellation. This becomes 2 on the bottom. Now you have a constant on top and a monotone increasing function on bottom. So you are in what I call obvious land, and you don't need to do anything else. It's what? 0. Likewise over here with the first one, that cancels with that. And again, you have 1 over n, which ends up being 0. Oops. 0. Come on. There. Which is 0. That's it. You're done. Right? The real challenge with the limit method comes when you don't necessarily have a monotone increasing function on denominator or the numerator alone. For example, what if I asked you about logarithms? Remember, it's base 2 implicit versus n. Which one of those is your intuition now? Step 1, what's your intuition? Which one of these has a larger order of growth? N. So log of n is going to be big O of n. Right? That's what I want to show. That's my intuition. If I were to set up a limit, however, as n tends towards infinity, of log of n over n, I've got a monotone increasing function on the top, a monotone increasing function on the bottom. Am I stuck? What tool do I have to pull out of my calculus toolbox to solve this? Oh, okay, I think I heard it. Le Hopital. I have no idea. There's a diacritic there and something over there. I don't know, right? L'Hopital's law is what? You take the first derivative of the top, the first derivative of the bottom, assuming that they converge, blah, blah, blah. Right? Right? So, what's the derivative of n? 1. Ugh. What's the derivative of log base 2 of n? Careful. Yeah, there's I'm just going to call it c. 1 over natural log of 2 times 1 over n. Right? So this becomes some c sitting out front, limit as n tends towards infinity of 1 over n, which is 0. Conclusion. Okay? All right. What if I asked you about, say, f of n is 2 to the n, and g of n is 3 to the n? What's your intuition now? I've got an exponential and an exponential. Are all exponentials created equally? Probably not. My intuition tells me that this is big O of 3 to the n. All right? Let's set up our limit as n tends towards infinity of 2 to the n over 3 to the n. Oh, okay. L'Hopital's law. What happens here? You have a natural log of 2, natural log of 3, and you're right back where you started. 2 to the n over 3 to the n. Why? Derivatives of exponentials are what? The exponentials with some constant sitting out front. Right? So that's not going to get us anywhere. L'Hopital's law is not going to help. Okay? So, nope, nope, nope. Limit as n tends towards infinity of 2 to the n over 3 to the n. Don't bring out the big guns like L'Hopital's law first. Bring out the little guns. The little guns are algebra. What can I do with 2 to the n, 3 to the n? If there's a common exponent, what can I do? 2/3 to the n. Right? 2/3 times 2/3 is 4/9. 2/3 times 2/3 times 2/3 is going to be 8/27. 16/81. Right? Dot, dot, dot. What is this converging to? 0. Why? Because this is less than 1. Right? If it were equal to 1, it would converge to 1. If it were greater than 1, say 3 over 2, what would happen then? Infinity. Right? This is why if you earn 0.000000, if you only earn like a fraction of a fraction of a fraction of a percent, all you would have to do is wait long enough and you'd still be a billionaire. Right? Why? Because this raised to the n, as taking the limit as n tends towards infinity, has no bounds. This is going to be infinite money. Right? All you have to do is find a positive amount of money, a checking account or something that even pays you a fraction of a fraction of a fraction of a cent, and then go to sleep for 1,000 years and you'll still wake up rich. Right? It's that easy, right? You just have to sleep for 1,000 years. And then, of course, it's all gone because of inflation. So, defeated your purpose anyway. Right? Okay. Oh, thank you. Yes. And yes, L'Hopital. Oh, we've got the correct, maybe the correct spelling. Yeah, the correct spelling of it in the chat, but without the fancy diacritics on it. Right? I know that there's like a hat somewhere on L'Hopital, but anyway. So those are the techniques. Right? We'll get plenty more practice as we go along. But as we've already seen already, we've got a category of functionality here, right? We've got algorithms that are constant, order 1. We don't write order 5 or order 42. We also don't write order 0 because that would mean that it doesn't take any resources whatsoever. And if you're going to run a computer, it takes something, right? If you're going to run an algorithm, it takes something. Logarithmic, for example, binary search. We have linear algorithms, linear search, quasi-linear, which would be, say, quick sort, merge sort, tim sort, right? Those are the efficient sorting algorithms. We've got quadratic, selection sort, insertion sort, etc. We've got cubic, polynomial, exponential, and super exponential. But as we've already seen, right, anything quadratic and above is not at all, even on today's modern computers, reasonable for big data, like 2 billion integers here. It's going to take you 20 years to do that on a quadratic. You're always going to be looking for something that is linear or at best quasi-linear, right? So even though, yeah, it's polynomial, right? In fact, theoreticians, they love living in polynomial land. They love showing, oh, okay, well, we can do that in polynomial time. It doesn't matter that it requires n to the 12 or something like that. Theoretically, it's possible, right? But still, it's not tractable or reasonable in today's computing, right? Or tomorrow's computing, or computing 10,000 years from now. It's just that whoever gives this demonstration 10,000 years from now will not be using 1 billion. They'll be using some other gigantic, enormous number instead, and just still telling you it's going to take you 20 years to execute that stupid algorithm, right? Instead, look for one of these algorithms, right? Quasi-linear. Okay. Hopefully that's the takeaway. We'll get some more practice on Wednesday. And we'll also be looking at other sorting algorithms. In your lab this week, you'll be implementing all these sorting algorithms and then like actually testing them out, see how much time they take. All right. See you on Wednesday.